Students, welcome to my second class in nuclear physics. In our last class, we had done the very basics of nuclear physics. Actually, we have not even entered the world of nuclear physics. We were looking at the background which led to the development of nuclear physics as a subject. So, we talked about radioactivity. We saw like this. We saw that radioactive rays originate in the nucleus. We saw that radioactive rays consist of alpha, beta and gamma rays, and we saw that radioactive the beta rays, not the alpha and the gamma, they consist of electrons. So obviously this indicates that nucleus contains electrons because these gamma rays, which consist of electrons, are coming out of the nucleus. Students, this idea, as we had seen in our last class, indicate the fact that nucleus contains electron, and owing to this indication, scientists came up with the hypothesis that the nucleus consists of protons and electrons. So this is the proton-electron hypothesis of the nucleus. Now about the numerical attributes, the proton-electron hypothesis said that in a particular nucleus we have a number of protons, a minus z number of electrons, so that the total number of particles is twice a minus z. Now this is the proton-electron hypothesis, and this proton-electron hypothesis, see, as science developed, people found out ways and instruments by which the spin, the magnetic moment, such qualities of particles like the protons and the electrons. Protons and electrons, I think you know that they are called elementary particles. So magnetic moment, why magnetic moment? Magnetic moment because these are charged particles, and when a charged particle moves, because they are moving in a circular path, they give rise to a magnetic moment. So they will have a magnetic moment. They will have a spin associated with its rotation, because spin is related to the angular momentum, as you must have come across in your study of atomic physics. So these could also be measured. Then they had the approximate size of the nucleus also could be measured. The approximate size of electrons could also be measured by, of course, indirect methods. Then I think you are aware with the Compton's effect. So there is also the Compton wavelength associated with the elementary particles. So this Compton wavelength, and there is something called the nuclear statistics, or the statistics of elementary particles, which perhaps you are not very familiar with. Students, I would like to state that we'll come across this magnetic moment, spin and statistics as we proceed with our course, and we'll be more familiar with these terms and what they mean. Statistics, actually all particles are either Fermi-Dirac fermions or they are bosons. If they are fermions, they follow the Fermi-Dirac statistics, and if they are bosons, they satisfy the Bose-Einstein statistics. So this is just an introduction. Don't be worried if you are not understanding. We'll definitely do these things later on. So these things together, actually, they all indicated, all these indicated that proton-electron hypothesis of the nucleus is a failure. It failed because, see, magnetic moment was measured, spin was measured, size was measured, Compton wavelength was measured, statistics was measured, and all these measured quantities indicated that the electron cannot reside inside the nucleus. So if the electron cannot reside inside the nucleus, definitely the proton-electron hypothesis is a failure. So these are the things that led to the failure of the proton electron. For an example, look at this. This is nitrogen, where A is 14 and Z is 7. So A is 14. We know that A is the number of protons. So number of protons is 14 and number of electrons is A minus Z. So it is equal to protons. So what are the total number of nucleons? Nucleons means particles inside the nucleus. It is 14 plus 7 is equal to 21. Now students, all fermions are a certain category, as I have already mentioned. All fermions have half integral spins. So 21 into half is definitely an odd number. So the total spin of the nitrogen nucleus must be an odd number, and an odd number indicates that this nitrogen nucleus is a fermion. But it has been found that nitrogen nucleus follow Bose-Einstein statistics, and so it must be a boson. So this is one example how the proton-electron theory could not be explained, and definitely we will talk about it later when you learn about all the properties of the nucleus. So discovery of neutron. At the time, along that time, about 1932, neutron was discovered, and this led to the proton-neutron hypothesis of the nucleus, which was given by Heisenberg. It was proposed by Heisenberg about in 1932, I think, that the nucleus consists of the proton and the neutron. So magnetic moment, spin, size, Compton wavelength statistics, these again came to the view, and measurement of this actually showed that the proton-neutron hypothesis is acceptable, and so the proton-neutron is till now accepted as the model, or the as the correct structure of the nucleus. Of course, there will be other particles that as we come along. So now we talk more about the proton-neutron hypothesis. So from now on, we'll accept that we have protons and neutrons inside the nucleus, which is the PN hypothesis. So we know that any element is written like this. If I write it like this and like this, this is a proton, this is called the mass number, and is the atomic number. And the nucleus obviously contains Z protons and A minus Z neutrons. See, this is looking very bad. It should be A minus Z neutrons. So this is the picture as of now. Now we'll look at some other things. So this is like this, but then we found that the proton and the neutron are inside the nucleus, but there are no electrons inside. So we have already seen these things. And then electron doesn't reside inside the nucleus. This we are confirmed now. But then beta rays contain electron, and beta rays are emitted within the nucleus. The fact remains like this. The fact remains that what? that look at this second point. Beta ray contain electrons. Beta rays are emitted from nucleus. That means what? Electrons are emitted from inside the nucleus. But then electron does not reside inside the nucleus. Well, how? See, this actually can be said to be the real beginning of nuclear physics. So before this, people used to think that the nucleus is, first people thought it was just positively charged body. Then people came to realize that yes, we have protons which are positively charged particles and neutrons which are uncharged particle bodies. Still it remains that this is a positively charged body. But then if electrons are to be emitted here, there must be something about it. So this led to the question mark that how? So there must be something going on inside the nucleus. So they just delved into the nucleus, and we will be inside the nucleus for the rest of our course. So inside the nucleus, that means so many things came up as to how the electrons, that means they came to know that maybe if electrons come out from here, proton, neutron, actually electrons are born here and they come out. They cannot reside here, but electrons, they come out. I'm sorry, it's not the neutron, but the electron, they get created here and they get emitted in case of beta emitters. We all know that radioactivity does not only consist of alpha, beta, and does not only consist of beta rays. It may be alpha ray, it may be gamma ray, it may be beta ray. But for beta emitters, the electrons are created at the time of emission. That means what? That means a proton and a neutron, they do not always remain a proton and a neutron. That means the proton, if I take it out of the nucleus, yes, it's a proton. But inside the nucleus, what happens is that the proton and the neutron, they always interact in such a way, they interact so that electrons are emitted. So this is somewhat puzzling, I know, but this is the fact behind how nuclear physics became so important as a field of research. So one more point about this I'll be talking about. First let me clear my board. You see, first let us work out the expression for density of a nucleus. Density of a nucleus. Students, at this point I would like to tell you something. Look at this word. This word nucleus. Sorry, nuclear. So nuclear, C-L-E-A-R, this is nuclear. Let me exchange these two letters. What does it become? Unclear. So that's what you will always feel when you study nuclear physics. But then why? Unclear is because of its small size. Because when you have a very small size, first of all you cannot pinpoint where it is situated, because you see, if something is as so small, then its position is definitely not defined due to uncertainty principle. We always have a amount of uncertainty there. So there itself the uncertainty, the unclarity, all is not unclarity, lack of clarity, these things come up. So let's stop here for the part B of our lecture.